Hello, class. We're about to start on our next sections here. Actually, we're starting on sections 4.10 to 5.3 this week, the week of April 12th through April 15th. Okay, so for section 4.10, we're supposed to go to pages 473 to 475 and do 1 through 3 all. Now, what I'm going to do I'm just going to cover problem number 1, and then problem number 2 and 3 you all would need to do on your own. So first, let's turn to page 273. Okay, at 273 at the bottom of the page, we have this table and we have this statement here. It says, according to the National Institutes of Health, cigarette usage for 8th, 10th, and 12th graders combined for various years from 1991 to 2016 is as given in the following table. All right, so we need to go to the next page. It says, sketch a scatter plot of the data. Let T represent the number of years since 1991. Does the data appear to be linear? And explain. Okay, so we need to graph that table for part A. And then you all could plot the points inside of your textbook for when you all submit this to me. So let me go back to the previous page. And down here at the bottom, and remember this is actually since 1990. These what the years are set up to be since 1990. So that was a little bit of a typographical error. Okay, so we're going to go to add a table. So we're going to type in the numbers. We have 1, 4, 7, 10, 13, 16, 19, 22. But that last number is 26, not 25. Okay, now we have 53.5, 54.6, 57.4, 51.8, 40.8, 35.0, 31.2, 27, and 18.2. All right, so now we got all these values in. Now we have to look at our scatter plot here. This is our scatter plot. Now, we go back to the question here. It says, sketch the scatter plot of the data that T represents the number of years since 1991. It should be since 1990. Does the data appear to be linear? And explain. Okay, now we can look here. It does not appear to be linear because this doesn't even look close to being a straight line. So we can say this in a formalized mathematics way. We could say the data does not appear to be linear. Let me write that down for you. Okay. So this is 1A. The data does not appear to be linear because as the input increases, the output decreases. Then decreases. So no line will be close to the points. Actually, I made a mistake here. This is supposed to be the output is supposed to increase. It increases, then decreases. So basically, as the input increases, the output increases, then it decreases. So no line will come close to the data. So now, We'll go down here to B. It says use your graphing calculator to create a stat plot, then determine the quadratic and cubic regression equations for the data. Now, first of all, we need to write down the general forms of both of this, the quadratic and the cubic equations. Now we're going to do the general form. It'll be y equals ax squared plus bx plus c. Cubic is y equals ax cubed plus bx squared plus cx plus d. Now it's very important that you have these equations in order to be able to do it in Desmos. So now we're going to go to Desmos. I'm going to take this graph. Well, this is the graph. Okay, so remember we're dealing with y1 and x1. So we would do y1, and we have to go here to our tilde. And then we would do a x1, and then we have to square that. Because remember, we're doing the quadratic right now. Plus bx1, and then finally plus c. Now, if you look here, for our quadratic, I should have actually left a little room here. But let me move this over here. This will make it a little easier. Let's see if it allows me to move it over here. Okay. So for our quadratic, and we're going to round to 3 decimal places. So we had a quadratic equation, and it'll be a negative 0.040 x squared. Well, supposed to be y equals negative 0.04 x squared. And then b is negative minus 0.519 x plus 57.333. So this is the quadratic form. Now we're going to look for the cubic, our cubic equation. So we have y1, we get our tilde, then we will have a x1 cubed, then we will have plus b, then we still would do x1, but this one would be squared, plus cx1 plus d. Now, we have our values here. So the cubic equation, remember we round into 3 decimal places. So it'll be y equals 0.006 x cubed minus 0.276 x squared plus 2.004 plus 51.985. So that is the quadratic and the cubic equation. Okay, now that takes care of, this actually takes care of section 410, but there is one thing that we need to change because they told us up here, let me pull up the book again. We have to change our variables because they tell us let t represents the number of years, and then we can also use g because they tell us to use g here. So we're going to rewrite this quadratic equation. So y will become g of t. And then these numbers will remain the same, but the x's will become t's. So this is the form they want it written in, with g and t. Then the same thing down here. You have g of t is equal to 0.006 x cubed. Supposed to be t cubed. Minus 0.76 t squared plus 2.004 t plus 51.985. And this is the formula here. Now, we're done with 410. Now we're going to go over to 5.1. Let's take a look at what 5.1 is. Page 496 to 498. And this problem is 1 through 4 all. So first we need to turn to page 496. Let me expand this out. So we got page 496. And remember, it's 1 through 4 all, but I'm not going to do all 4 problems. I am going to, let's see, which problem should I do? I think I'll do problems 2 and 4. So we will need to go to the next page, which is 497. So we look here at number 2. Let me make this a little longer. Okay, there we go. It says, sketch the graphs of the following pairs of functions on separate coordinate systems. Use labels or colors to differentiate the graphs. Verify your sketches using your graphing calculator. Okay, listen. Let's just go right to the graphing calculator. What I'm going to do here, I'm just going to take this away. So there'd be no other graphs here. So I'm just going to make the f of x be y and the g of x be y as well. So we could do y is equal to 5, and then we could do divided by x. Okay, we see that graph here. I'm going to expand it, but we know that this graph is blue. So now we could do y equals negative 5 divided by x. And then now we have the graph being in green. So let me expand this here. So I think I want to change this here. So with that being that there, let me start it off with, let me start off at 0. Let me go to the y-axis. Let me do just negative 20 to about 20. All right, let me see how this graph, well, it still looks pretty close together. But as you see here, you can see the differentiation here. They look almost the same, except for the blue graph y equals 5 over x. You notice this graph in this direction here. It doesn't touch the x-axis or the y-axis. And then here, we have the green values here, which is a negative 5 over x. Okay, so this would be somewhat like the sketch of our graph. Let me see something if I could. Now you see how it's not as close as what it seems. So this is a sketch of the graph. See if I can move this over. Okay, great. Now we come here to B. Describe how, says describe how the graph of G can be obtained from the graph of the function of F. All right. Let me pull up the camera. So this actually would be 2A. And then we could say the change in sign results in opposite output values. The graph of G is the reflection of F about the x-axis or y-axis. Okay, now we move on over here to problem number 4. So on page 498. All right. For problem number 4, it says the speed limit on Route 66 in Parts, Arizona is 75 miles per hour. If you maintain an average speed of 75 miles per hour, how long will it take to make a 350-mile trip on Route 66? Okay, so first of all, we need the distance formula. Now, the distance formula is equal to rate times time. Or sometimes it's written as time is equal to distance divided by the rate. Okay, so now it looks as though we're given the values where we would need to utilize this time equation. So we had time is equal to, now the distance according to these directions is 350 miles. And then the rate, and that's the traveling rate or average speed, is the 75 miles per hour. So now we divide this out, and we could do this one of two ways. You could rewrite this as a fraction, like basically here, you could divide both of these by 25. Your denominator would be 3 here, and then you could use your Desmos. As a matter of fact, instead of doing all the dividing, you can use the Desmos calculator. With 350 divided by 75, it gives you the decimal. But if you want it to be a fraction, just hit this here, and this would be actually 14/3. Now, 14/3, if we make it into an improper fraction, will be 4 2/3 hours. So now, I don't know if they wanted this in, or they just said how long. So they didn't say whether or not they wanted this in hours and minutes. But let's assume that they do. So we know this 4 here would be 4 hours. But we will have to change this 2/3 hour into minutes. So we know it's 60. So this is 2/3 hours. So we know it's 60 minutes in 1 hour. These hours will simplify out. 2 times 60 is 120 divided by 3, which is 40. So it's 4 hours and 40 minutes. All right. Now we move on to B. It says write an equation that defines t as a function of r, in which r represents the average speed in miles per hour and t represents the time in hours to complete the 350-mile trip. So this is still the time formula. Time is equal to d over r. So we know that the distance is 350, but we don't know what the r is, so we will leave the r the same. And we're done, because they wanted us to write this in terms of r. Now we come into C. It says complete the following table for the equation you determine in part B. So we have 350 over r. So now let's take this table. So we know this is r, this is t. So you have 25, 35, 45, 55, 65, 75, and 85. All right. So we have these values here. So all we have to do here is substitute in these values in the denominator of the fraction. So we could go to our calculator. And what we could do is this here. We could go ahead and say 350 divided by, and then you could say 25. That'll be 14. You could change your 25 to 35. That'll be 10. 35 to 45. So we wrote this as a decimal rounded to one decimal place. It'll be 7.8. Then we could do 55. Rounded to one decimal place, it'll be 6.4. Then 65. One decimal place, it'll be 5.4. 75 be 4.7. And then 85 be 4.1. So these are all the values for the table as far as how much time it would take. All right, now D. As your average speed increases, what happens to the time it takes to complete the trip? Well, if you're going to speed up, you'll get there faster, which means that time would decrease. So you could say it decreases. But it decreases slowly as R increases. All right. Now we go to E. It says, as your average speed for the trip gets closer to zero, what happens to the time it takes to complete the 350-mile trip? The time increases very rapidly as the rate approaches zero. And now we look at F. What is the practical domain? Now, we know here, according to this table, even though we don't see some of the values here, but according to this table, when we look at speed limits, first of all, we know our rate has to be greater than 0 because there's no negative speed limit. So we know it has to be greater than 0, and we know it can't equal 0 because if it equals 0, that means that the car is not moving. So first we know it got to be greater than 0. But now, the highest speed limit I've ever saw on a highway was, I believe, 85 miles per hour, which we have here. So it could be, the rate could be less than or equal to 85. Because I have yet to see any place in the United States where they had 90 mile per hour speed limit. And so I know, like in Germany, the Autobahn, but that's a whole nother situation. So just to let you know that that is the practical domain. Now, it says G. It asks us to sketch a graph. Now, according to, actually, we didn't do that. So we need to do a quick table here. Let's do a table of the values. Let me scoot this over here so we can look at these values. So let me add a table. So we went from 25 to 85, 25, 35, 45, 55, 65, 75, then 85. All right. So 25, we got 14, 10, 7.8, 6.4, 5.4, 4.7, and then 4.1. All right, let me turn off this graph here. Okay, now, you look here at these points. If we want to see a line, there's a couple ways we could do the line. We can do the wheel here. Well, actually, it's already set up. Okay, let me go back here. Okay, now if you look here, this looks exponential. So what we could do, we could try and see how this is exponential. So we know exponential is y1, the tilde, tilde, AB, to the x1 power, and hit the log mode. Okay. And as you can see, the graph is sketched. So you get a good representation of the graph here. It is an exponential graph. Okay, now we go here to the last question. Again, as you see here, we have the graph, and you see that it almost fits perfectly. So now that would take care of G. Now we want to look at H. Let's take a look here at H. It says, what are the vertical and horizontal asymptotes of the graph of the function? Now, if we look back here at Desmos, if you notice here, this graph actually does not, we have to look at it not crossing the X and Y axis, because when we're doing a problem like this, remember, we're doing things that are practical. Now, since we're doing distance is equal to the distance times rate times time, no, we are not dealing with negative numbers. We're not. So if you look here, this graph is not going to cross 0, even though you see this graph is crossing 0 here. I would have had to put a restriction on it, but this graph is not supposed to cross 0, or is not supposed to hit the 0 on the x-axis. So basically, your horizontal, and I'm going to abbreviate this for H. Your horizontal asymptote is T is equal to 0, because that's the restriction on it. And then the vertical asymptote is where R is equal to 0. So if you look back up here at the equation that we have, if you put in 0 for R, we know that that would not work. And we know that T would never equal 0, according to this fraction here. So that is basically the horizontal and vertical asymptotes. Now, we will